Welcome to our MATLAB exercise on one-dimensional gridding. So first let's talk about a little bit of motivation, and this will be a bit of a repeat from some of the stuff we talked about in class, but just to make sure we're on the same page, we'll go through it here again. Okay, so conventional MR acquisitions collect data on a Cartesian grid in K-space, as we've seen before in lecture. And in that case, Reconstruction is just a 2D discrete Fourier transform that is embodied by a fast Fourier transform algorithm. Now, while Cartesian acquisitions have lots of advantages, such as, for example, fast reconstruction times, because you can just directly use an FFT without any gridding. They are relatively immune to system imperfections, such as eddy current-induced timing errors. Imperfections. Because I can't see what I'm typing very well, I'm just going to leave that. You can see what I wrote. And then they are just generally very robust, right? They're robust to lots of different types of image artifacts that you might find, including chemical shift is not as big an issue with 2DFT acquisitions as it is with non-Cartesian acquisitions. Okay, so there are other possibilities, of course, that bear advantages for certain applications, especially in real-time imaging. The most common two non-Cartesian acquisition trajectories are spiral and radial. So spirals are useful for imaging motion or dynamic changes. So they're used a lot in cardiac imaging and in fMRI. Okay. So the other trajectory are projection or radial trajectories, where you collect a set of radial lines in K-space, right? And these behave very well when undersampled, so they can be also useful for real-time imaging. They've also been used for cardiac imaging. They haven't really been used for fMRI because they still have limited volume coverage for the brain. But they have also been used for contrast-enhanced imaging, which is for which they have the advantage that you always collect part of the center of K-space with each line, right? Since each line passes through the center of K-space, or each projection passes through the center of K-space, you always sample that contrast-enhanced signal, which is changing potentially dynamically during the readout of a single image's data. They've also been used for short T2 imaging, so in that case what you do is you use a center-out radial that starts in the middle of K-space and then moves out. Of course, then that means you have to collect more projections. So you start here and you move out, but of course that means that you're not getting the other half of K-space with each projection, so you've got to do more lines in that case, twice as many lines in that case. And of course, this is the type of acquisition that we effectively have in CT and PET acquisitions. Okay. Now the problem with these, of course, these non-uniform trajectories, is that the data falls on a non-uniform grid. So how do we reconstruct it? Well, in class, of course, we talked about using gridding for this. So gridding is the most common way to reconstruct images acquired on these non-uniform trajectories. Okay, so let me change my font size here so I can fit more text on here. Okay, so the steps that we take in gridding, as we talked about in class, are to first density compensate the data. And generally, with all useful trajectories in MR, we have a higher sampling density at the low frequencies. So we have higher density near DC, and so those frequencies are going to be overemphasized if we don't do any density compensation. The second step then is to interpolate the non-uniform data onto a Cartesian grid, and that is done by a convolution operation or a discrete convolution operation. The third step is to take the inverse d of t. That's a step with which you're very familiar now. And the fourth step is to deapodize the data, to remove the effect of image intensity weighting due to the convolution, the k-space convolution. Okay? So in this exercise, in this MATLAB exercise, I'm going to walk you through implementing each of these steps for a 1D problem. Okay, so let's get started. One second.
Hi.
Okay, so now let's get started with the code. What I have here in this MATLAB window, let me kill some stuff off here. Close that to give us some more space to view this. Okay, so what I have here in this MATLAB window is the template for this exercise, the template.m file, the script for this exercise, where I've essentially removed all the stuff that we're going to fill in today as we go along so that I can add it while explaining it at the same time. Okay, so but I've left in the stuff that actually defines the data, right? Because that part is actually agnostic of the gridding stuff, which we're actually talking about. But it's worth going ahead and starting with this. Okay, so we'll go ahead and run this script. I put in a preliminary, an early return here into the script. I'll change the folder. Okay, very good. All right, so now I've got my image from which we're going to take a single one-dimensional line. Okay, so I'll go ahead and plot that that image, which looks like this. Okay, it's a profile of a Shep-Logan phantom, of a 256 by 256 Shep-Logan phantom. It's a 1D profile through one of the directions. Okay, then the next step is to calculate the non-uniform k-space locations on which we are going to acquire the signal from this phantom. So I've got that defined here, right? So I basically take a bunch of points, I do a cumulative sum to get the cumulative k-space trajectory, and then and define it here. So there's not too much more to say about that, except to just show what it looks like. Okay. So this is an illustration of the trajectory sampling locations in one dimension. In the x-axis, I've got spatial frequency, which is an integer here. And on the y-axis is just denotes whether or not there is a sample at a given location, okay? So you can see that this is a stem plot, so each one of these little spikes corresponds to a location that we are sampling. And what you can see here is that the density of the sampling increases as we get closer and closer to the center of k-space. So you can see then that we're going to be overemphasizing signals at the center of k-space. And if we zoom in, of course, then we can see a little bit better, right? The density is higher and higher as we get closer to DC. Okay? And so each of these stems represents one location where we acquired the signal. Okay, so I'll remove that return. And then what we do is we have to synthesize the data, right? So we already know what the true image is because we defined it, and we also know the k-space trajectory. So using those two variables, we have to get the image data. So we'll build a matrix, a 2D matrix. This is in one dimension. This is really the only case when you can explicitly build a matrix like this is when you have a one-dimensional signal that you're trying to get this, or a one-dimensional signal. So what we do is we build the Fourier encoding matrix, which is a complex exponential matrix, where we have essentially the Fourier kernel here, right? So it's going to be the non-uniform k-space trajectory, which is going to be a column vector. So it's going to have nk rows. And then the minus n over 2 to n over 2 over n indexes the normalized spatial locations in the image, right? So the rows of the A matrix will correspond to different points in k-space, while the columns will correspond to different points in the image. Okay, and so then to get the data vector, what we have to do is just multiply A times M. Okay, so we'll go ahead and do that, and then I'll probably go ahead and plot then A times the image, I'm sorry. A times image. And so I'll return this here and run it to that point. Okay, so there are my sampling locations again, but then I'll go ahead and plot the amplitude of the signal. Okay, so you can see that indeed, as we would expect, because we know that real-world signals are concentrated near DC in the frequency domain, we have a lot of signal near the center of the readout, and then that decays away as we move out. Okay, so that kind of makes sense in terms of where the signal's energy lies. Okay, so let's move on. So we're going to go ahead then and start right away with the interpolation of the data onto a 2 times oversampled Cartesian grid. So it'll be a uniform grid in one dimension, right? A rectilinear grid in one dimension. So in this particular example, we're going to use an oversampling factor of 2. We're going to use a neighborhood of 5 samples around each point. And we're going to use a Kaiser-Bessel beta of 11.5. And so what I've done then is I've created this Kaiser-Bessel gridding function that takes the k-space locations that each data point lives on, and then the data itself, and then the size of the grid of the truncated, the target grid that we have, the oversampling factor, so the total size of the grid is going to be n times OS in each direction. The width of the Kaiser-Bessel kernel, again in samples, which then of course also defines the size of the neighborhood in the direction in this one dimension, and then the Kaiser-Bessel beta. So those are the arguments that we're going to pass to KB grid, and what should be returned from KB grid is the gridded data on the Cartesian on a Cartesian 2D oversampled grid. Okay, so let's jump into the Kaiser-Bessel grid next. Okay, and here we are in the KB grid function. So again, you see the same, I've used the same names both in the master template script and also in this function for all the different variables. So again, K is the k-space locations. We expect those to be values that go from minus n over 2 to n over 2. They're not necessarily integers though. They can actually be floats or anything. The D will be the data, right, that we synthesized from our 1D profile. OS is the grid over sampling ratio, which in this case is 2. W is the width of the Kaiser-Bessel kernel in k-space, which is going to be 11.5. And B is going to be W is the width in the kernel in k-space, which is 5 in this case. So that's the size of the neighborhood. And then B is the Kaiser-Bessel beta parameter, which determines the shape of the Kaiser-Bessel function. And here we specify that would be 11.5. Okay, so first we detect the number of k-space locations that we have to grid from onto our Cartesian grid. So we have nk k-space locations just by taking the length of k. If you have a 2D problem, then k is going to be a number of the rows, by my convention, would index the locations along the trajectory, and the columns would index the different spatial dimensions, x or y. Okay, so nk here is length of k, and we can do that because k is a one-dimensional vector here. So we know that the length has to be equal to the number of k-space locations. Okay, then dc, we have to initialize 2. So dc is what we're going to call the Cartesian vector in this case, the Cartesian grid of output points that we're going to grid our non-uniformly acquired signal onto. So in this case, we're going to instantiate it to be zeros, a 1D vector of zeros. And so we have and the length of it is going to be the oversampling factor, which is 2, times n, which is the length of the signal. I believe we set it to be 256, right? So it's going to be a 1 by 512 vector here, okay? And then what we're going to do is we're going to loop through every location along the trajectory, right? So that's what this outer loop is looping over. And then we're going to, for each location, for each data point and location along that trajectory, we are going to find the grid points on the Cartesian vector, in the Cartesian vector, within a W point neighborhood or surrounding each sample. Then we're going to calculate the kernel weights at those grid points, where those kernels are, the kernel is going to be centered at the acquired data point, and then it's going to fall off as we move away from the acquired data point, where the weight is then going to, in the calculated weights, of course, will depend on the distance from the data point to each of the points we are gridding onto. Then we'll take the weighted data and add these weights and multiply them times the data and sum that into the total Cartesian vector. Okay, so the first step is to find the grid points in a W point neighborhood. And so the way we're going to do that is by we're going to round these of the oversampling factor times the k and k space location, right, which goes from minus 256 to minus 128 to 128, times minus of W minus 1 over 2 up to W minus 1 over 2. Okay, so this is doing a couple of things. First, we get a vector of offsets within the neighborhood, right? So for example, here we have 5 points in the neighborhood, so this vector here is going to go from minus 2 to 2 in integer increments. Okay, it's going to go minus 2, minus 1, 0, 1, 2. And to each of those points, we're going to add the offset corresponding to the current location in our k-space trajectory. But we also have to scale that by the oversampling factor to get it into the correct units for the oversampled grid. Okay, so we calculate these offsets, and then we add to that the coordinate that we're at in the k-space trajectory. Okay, and then that'll give us our grid points surrounding this data point in a W point neighborhood on the Cartesian grid. Okay, and so now at each of those points we have to calculate the kernel weights. Okay, and this is going to be given by 1 over W, which is the beta of the kernel, and it's going to be a first, I believe it's a second zeroth order Bessel function of the first kind or something like that. Then takes beta times square root of 1 minus OS, the oversampling factor, times k of II minus kn. Right now you can see that we're actually subtracting back off that shift, square that, square root, close paren. Okay? So this is the argument. This square root term is the argument to the Kaiser-Bessel function. Okay, so the next thing we're going to do then is add these weights, multiply these weights times the data, and then add them to the grid points. Okay, and so and what we have to do then is also add n over 2 minus 1, n over 2 plus 1 to our kn's, right? Because these are going to index from minus 128 to 128, but actually we need them to go from 1 to 256. So we have to add that integer shift to them, os times n over 2 plus 1, to those locations to get actual indices into the matrix, right? Instead of just k-space locations. Okay, so those are the indices to which we are going to put to which we are going to add the signal. And so what we do is we take those indices, right? We're going to put our signal at those indices, weighted by the kernel. But we also have to make sure that we're not going to be out of bounds of the matrix, right? So we have to make sure that we're only doing this if those indices are at least 1, right? Because MATLAB starts indexing vectors at 1, and they have to be less than or equal to the oversampling factor times n, which is the last entry in our gridding vector. Okay, of course we're going to have to duplicate those indices then to this. Remember that we have to have DC on both sides of the summation, right? This is like a plus equals operation in C, but in MATLAB we have to do it explicitly. And this is because we have to, if we have multiple points that are close together, their signals have to add together, right? We have to continue accumulating all their signals. So we want to take the signal that was already there and add to it the signal from this particular new point. Okay? And so what we're going to do then is then take our weights. Okay, weights of n's is greater than 0. And n's is less than or equal to os times n times d, the data point, d of II. Okay? So that is what we will do here, right? So again, we add these checks here that making sure that all the entries that we're actually going to use in the index vector are at least 1 and no greater than the last index in the vector. We have to do that for the Cartesian grid and also for the weights, right? So if there's going to be one that's outside there, we also have to discard that in the weights. Okay? So that should complete this function. So now we should be able to go back to the template function, and we should be able to go ahead and run this. So we're going to run this, and then we, of course, if we want to look at an image, we have to inverse FFT the gridded data, right? And so we're going to do this by taking IFT, which is a function you've already defined in previous exercises. And we're going to take the inverse Fourier transform of the density of the gridded data, DC. And then we're going to have to truncate that image to be the same field of view as the original. So that means that the center n points are what we want, right? So we need to skip the first n over 2 points, and we need to skip the last n over 2 points. So we'll get that by taking image of oversampling factor minus 1 times n over 2 plus 1 to n to the vector minus os minus 1 times n over 2. There are other ways to do this, but this is one way to just grab the central field of view that we have reconstructed. Okay, the part of the field of view that we actually care about. And then let's display it and see what it looks like. Okay, so here's what we get. And so we have the original object plotted in blue here, and then we have the gridding result in red. And you can see that just as we talked about in class, the red is much smoother than the true image, right? It looks like sort of a blurred version of the true image. And that's because we have not density compensated the data, right? So we've way overemphasized the low frequencies. And that's equivalent to effectively low-pass filtering the data, okay? So we need to fix that. And that's the next part of the script. So if we scroll down here, then in the next part of the script, I can't calculate the analytic density compensation. That's going to be a trajectory-specific thing, so we're not going to go through it in detail here, but suffice to say that this is the analytic density compensation. Then we need to apply that to the data, right? So we need to take the k-space data and directly apply the sampling density compensation to it. So we'll do that just by taking the data and directly multiplying this vector row by it. Okay, and then we're going to do the same operation, the same gridding operation. Again, we haven't changed any of the arguments except for the data, right? So we first density compensated the data, now we're going to grid it. Okay, and then we have to do the same IFT of the density compensated data, density compensated and gridded data. And then we're going to truncate the image down to the central field of view. And so we'll do that by just copying the same lines down there. And then we'll return after we plot that. Okay, so now what we should see is a density compensated reconstruction where we have where the data now looks not low pass filtered, but it's still got this weighting here on top of it. And so what is that? That is due to the fact that we have convolved the data in the k-space domain by the Kaiser-Bessel kernel. And that convolution in the k-space domain corresponds, of course, to a multiplication in the image domain of the gridded image by the Fourier transform of the Kaiser-Bessel kernel. And so that is what is giving us this image intensity modulation here, but at least our frequencies, our sharp features have all been restored by doing density compensation. Okay, so that looks much better than the previous result where we had this blurring of it, but we still need to de-apodize it. Okay, so we're almost there. Okay, so we don't have to do any more gridding anymore because now we have the gridding result that we want. We just have to de-apodize the final image that we reconstruct. So we're not going to have to do any more gridding again. What we want to do now is calculate the inverse Fourier transform of the Kaiser-Bessel kernel that we used to grid. Okay, so we're going to do that by calculating the kernel itself. We're going to initialize it to zeros, os times n, comma 1. Okay, that'll be a vector of zeros to begin with. And then in the middle of that Kaiser-Bessel kernel vector, we are going to fill in one single set of samples. Okay, and so this is going to be, this is a bit long, but it's going to be 1 over w times the size of the neighborhood times Bessel I 0 comma b times square root of 1 minus. So this should be the same arguments as for the, sorry, minus, should talk and type at the same time. W minus 1 over 2 up to w minus 1 over 2 dot divided by w over 2, close parent, double close parent, squared, close the square root parent, close the Bessel I parent. Okay, so this is going to be the same exact expression as we used in the KB grid function, but it's just going to be evaluated in the middle of the signal matrix, right, in the middle of the Cartesian grid. Okay, so this guy is going to be centered at DC instead of being centered at any given data point location. And then, of course, we can get to the image domain version of that by taking its inverse Fourier transform. So now this is the function that we need to divide out of our image. And we take a dot transpose so that we can directly multiply it, or divide it out of the data. Okay, so now we have, after we take this inverse Fourier transform, we now have an image domain, the image domain copy of the kernel. Okay, and that is what we need to divide out of the image. Okay, so to get the deapodized image, the deapodized and density compensated image, we take the density compensated image and divide out the Kaiser-Bessel kernel. So we're going to take the center, because we define the Kaiser-Bessel kernel again on an oversampled grid, we have to take the center field of view of it before multiplying it so that we don't get any matrix size problems. So we're going to use the same expression for extracting the center of the matrix, or of the vector, as we did for the images. We divide that out, and then we'll display that final result, which hopefully will look just like the true image. Okay? I'll clear my workspace, and then just go ahead and run it. And indeed, we do see that in this case, when we do the deapodization, we do get the very close to the true image back. Okay, it's not perfect, but it's very close. Okay, so we have our first reconstruction, which did no density compensation, and we got essentially a low-pass filtered version of our image because we had so much oversampling of the center of k-space, so the low frequencies were overemphasized. Then we did a density compensated reconstruction by multiplying by the inverse of the sampling density. So we downweighted the points in the middle of k-space where the signal was where the density was much higher, and that fixed that blurring. But we still had the apodization left over from the k-space convolution with the Kaiser-Bessel kernel. And then when we took the Fourier transform of the Kaiser-Bessel kernel and divided that out of the image, that fixed that image intensity modulation. And so now we get an image with the same intensity as the original image and the same features. Okay, so that concludes this MATLAB exercise. I hope this helps you getting started with the future work here. Thanks very much. Bye-bye.